So my name is Chris. My username on social media is ProgramMax. The way this talk works is kind of more comfortable if you feel free to ask questions. So you don't have to wait till the end. If you have a question on a particular slide, just go ahead and raise your hand or sing and dance, whatever you want to do. Okay, so let's get started. So this is the roadmap I want to talk about today. I doubt we'll have time to cover everything, but that's actually okay because those last 2 points, raw pointers and templates, you don't super need to know them right now. And I go into like really ugly details about them just to try to make them less scary. But if we don't get to those slides, it's no big deal. Just be aware that what I'm going to show you in those slides, you probably don't want to write in your day-to-day work. So, if you go back later and look at the slides, don't use that as an example. All right, so let's start with free functions. So I'm going to pick on Java a little bit, and that's not because Java's bad. It's just easiest for everybody to read. And I want to use Java as examples that are clear, whether you're coming from Python or Java or JavaScript, whatever. So here's 2 cases of pure object orientation that happen in Java that don't really make a lot of sense. So the first one is your entry point, the static void main. That doesn't actually have to be part of a class, which is why it's static in the first place. Here it's related to class Hello World app, but it could have been in any class. So that really proves that it's not actually connected to a class at all. And further, we never had a chance to create a new instance of this class, so it couldn't have possibly been related to the class. Like, there's no way at all. So that was just, we had to do it because Java is pure object-oriented. Same with this. The max function to get 2 integers, that doesn't have to be a class at all. You pass in 2 integers, it returns the max of the 2. This has nothing to do with the class. So really here, the class is just a namespace. So this is an example of where pure object orientation isn't really perfect for all situations. And if we translate those exact same things into C++, we wouldn't have done object orientation. We would have just made them free functions. So that they're free here means not like free as in speech or free as in it's no cost to performance. It just means it's not related to a class. Okay, include and linkage. So Java, Python, you're kind of used to these import things, and the idea is some other file has it, let's go fetch it from that other file. It's the same concept in C++. You'll notice I kind of did pairs here. So the top one is sort of like getting a system library sort of thing, and the bottom one is here is some of our code. And in C++, you typically do those a little differently. If it's like a library, you're probably going to be using those angles. And if it's your own thing, you'll probably be using quotes. This is roughly how C++ is built. So I'll have 2 code files, a.cpp and b.cpp. Each of them are individually sent to an instance of a compiler and compiled completely independent of each other. So each of these is called a translation unit. And then the result of that compile is an object file. All the object files are then gathered up together and sent to the linker. The linker combines them and makes the program for you. So that kind of results in there being a compile phase and a link phase. And I'm saying kind of here because the lines get a little bit blurred. There are times when you do link time optimization where the compiler passes extra info over to the linker, and then the linker can start rearranging functions how it wants. But this is roughly how you'd want to think about it. So by default, because we had sort of separate translation units and they don't know anything about each other, by default, there's no way for the functions or classes or whatever in your files to actually interact. And we probably want to interact with them. We'll get to that in a second. But remember, the linker is going to combine all these things. And maybe some of the functions I'm writing, I don't want to expose to the other translation units. When they get combined, maybe this one was supposed to stay just within this file. So there's 2 ways of hiding it from other translation units. One is to put your function in an anonymous namespace like this. And the other is just to put static in the front. Static is kind of the old way. We prefer the anonymous namespace in Chrome. So I mentioned that if you have two separate code files, you probably want to use functions from the other one or the class from the other one. So the way that works is you'll have, for example, computeharmony.cpp, and you pair it with computeharmony.h. That's the header file for the actual translation unit. And in the header file, you're going to be doing forward declares of what you want to expose. So for example, if I have some function compute harmony, I'll say in the .h file, hey, I promise there's a function called compute harmony, and you just have to trust me on it. And at link time, the linker will know where the function is and it'll finish the call. But in your code, if you try to call this function, you can just trust me that the function will exist eventually at link phase. So here's what that would look like. We have our .h file. All it does is forward declare there will be a function. This is what the signature looks like. Then we have the CPP file. It includes the .h file just to make sure the forward declare and the actual function link up. And then that's where you put the actual function body. And then in the other CPP file, you also include that same .h file. So when we're compiling, it doesn't know what function it's going to call. It just knows what the function should look like. But at link time, it'll know what the actual function is going to be. Any questions so far? Great. OK. So back to our little picture. This is kind of what it'll look like now. We used to have a.cpp and b.cpp. Well, now we're going to pair a and a.h. Sorry, not compare. Combine, whatever. OK, so then we mentioned there's the two ways of including. There's with quotes if it's our own file, and then there's the angles if it's like a system file. That happens at a pre-processor step before the actual meat of C++ happens. So what this ends up doing is effectively copying and pasting. So it'll go open that file, copy the whole content of the file, and then paste it on the line that was including it. It's not 100% true, but that's like 99% true. OK, so we're going to run into a little problem with this copy-paste thing. And I need to set up a scenario to show you what this problem is going to be. So previously, we were just doing a forward declare of a function. You're allowed to forward declare the same function 20 times if you want. That's OK. But a define is different from a declaration. A define is saying this is the actual thing, and you can't redefine something. So if I have my header file, and I put this class music type in it, this is now a definition of that class. It's not just a declaration that there will be a class. So now I have jazz.h, and it includes musictype.h. Then I also have classical.h, and it also includes musictype.h. And then I have playmusic.cpp. If that includes both jazz and classical, we kind of created a diamond where we've included this musictype.h twice in this file. And then that means this class has been defined twice. So the compiler will yell at us and say, whoa, 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 you're not allowed to redefine classes, even if they're the exact same. I don't know if they're the same yet. So it'll yell at us. So we need some way to protect from this. So what we do is, actually, I already described all that. So what we do is this what's it called? Protect inclusion guards. That's what it's called. So if the file name is musictype.h, you just do this if not defined musictype.h, define musictype.h, which means the very first time it'll enter this. But the second and third time, it'll hit that, oh, wait, it has been defined. We don't want to do this whole thing a second time. So that's kind of the standard C++ thing. You see this in all of the header files, and it protects from that multiple inclusion. OK, destructors and scope. So imagine we're in Java land, and we have a class that represents some sort of resource, like a network connection or a database connection file, something like that. We don't have deterministic destruction in Java, which means if I am currently using this file, and then I'm done with it, and I get rid of my reference, the reference is still in memory until garbage collection happens. I don't know when garbage collection is going to happen. It might never happen. And so I don't actually know when the destructor is going to get called, so it may never actually release the resource. So that's kind of a problem. Java offers us this finalize. Oh, and by the way, that's, I could have called .close on it, but what if I forget? You would rather have this automatic protection that as soon as I'm done using it, it automatically cleans it up. So we could add this, finalize overload, but that kind of runs into the same situation. I don't know when it's going to be finalized. I don't know when the garbage collector is going to come. So that's not really solving the problem. C# added the using keyword, and then Java 7 added automatic resource management. And that gives you a way to say, like, within this range of code, I'm going to use this resource. And when I'm done, I want you to garbage collect just that resource. So it kind of solves this problem, kind of. But now we have a separate problem, and it's actually kind of similar. The responsibility is on me to use this using keyword. And if I forget, I've fallen back into the same issue. It's the exact same as if I had forgotten to call .close. So we didn't really solve the problem here. So that's where C++ destructors come in. These are deterministic. So this is an example of a destructor. You can put whatever code you want in there to clean up your resource. And as soon as that object is destroyed, if it goes out of scope or anything like that, this destructor is going to be called. So for example, if I have a function and then that's my class that I have, as soon as we hit the closing bracket here, or brace, this is going to call all the destructors for all the objects in that function. And you can actually just insert these wherever you want to force local destruction. So that way it gets cleaned up between the first part and the second part. So the idea here is anytime you want to represent a resource, you now have the ability to do that. I gave examples: network connection, file, GPU is the one I'm going to use because that is less likely to throw an exception. And in Chrome code, we don't use exceptions. So it kind of fits the slides better. For this next topic, RAII. So I just showed you that destruction lets us represent a resource. Deterministic destruction does. If we construct an object while taking that resource, now the entire object is an actual representation of that resource. So RAII means resource acquisition is initialization. The idea being that if we have constructed this object, it is initialized, it's ready to go. So this is old code that you might have seen. This is the opposite of RAII. So we have a GPU instance, and we call .open to get this GPU. And that .open call may have failed. And then we have to call, well, if it failed, do some error handling. This is the opposite of RAII because we tried to acquire the resource, but we failed. The initialization isn't acquisition or acquiring. So this is the opposite of what we want. A better way would be to have a function that always succeeds, and it just returns an instance of our GPU class. And now we don't have to track, did it fail, did it not? In this function, it will always succeed. The class itself doesn't need to know if it could have failed. And if we didn't have the option for it to always succeed, like maybe it could have failed, let's not store it in the class. Let's use something like base optional. Base optional will either be the class you wanted it to be or nothing. And so that way, our GPU class doesn't have to track, did I fail to initialize? Okay, pass by reference and value. This one's a little weird because a lot of other languages, they try to, with garbage collection and all that, they try to manage this for you. And you don't really get a clear view of what is a reference and what isn't a reference. So I'm going to continue picking on Java. I love it, but it's really good for examples. We have this function, add to dictionary, and we pass in a word. Makes sense, right? If this was C++, that would be passed by value. And what would happen is when we call this function, it would make a copy of the word that you passed in. And then inside our function, we'd be operating on that copy, not the original value, which means we can make changes and all that. And remember, I told you about destructors are called when the scope is closed. As soon as we leave that function, our copy is destroyed. That's how it would work if we had written it that way. The alternative to that is the exact same thing, except we put a little ampersand after our type, add to dictionary word ampersand. That is saying, I'm not actually taking a word, I'm taking a reference to a word. So in this case, if you call this function and you pass in some word, we are getting the reference to the original thing, and any changes we make will actually be reflected in the original object. This is actually pretty close to how Java works. In Java, even though we would have typed the other thing, behind the scenes, it's passing references around. So when we want to use this, imagine our word class is really heavy. It's really expensive to make copies. You don't want to make hundreds of copies as you make hundreds of function calls. And so you might be passing references around. The opposite of that idea is if it's really cheap to copy, the reference actually is an indirection. It says, here's the location in memory, jump to that location in memory, and then get the actual thing you wanted. So that extra indirection, that's not free. So if it was cheap to copy, like say an integer or something like that, you might as well have just copied. Oh, another thing I really want to point out, just because it's a reference, that does not make it memory safe. This is not garbage collected. It's just a pointer. That's it. Okay, so in the last slide, it was a word reference. I'm going to change that. Now it's a const word reference. What that means is the thing that I'm referencing, I don't want to actually change. Because remember, it had the option to alter the outside value. We probably don't want that if we're just adding it to a dictionary. So we can just throw the const keyword in there. That's pretty typical of old style C++, and this actually started changing in C++ 11. I don't remember if these slides get to that or not. Okay, so here are those 3 examples that I gave before, and I want to give a general guideline of when to use which. So the first one, const reference, if you don't plan to ever change it, and if it's kind of heavy to copy, go with that. A better way to say that is if you're just going to observe the value, that's when you use it. If you're doing a normal reference, non-const, that is if you want to modify the thing that they are passing in. So if you want to say like initialize all of these values or something. And then the last one, when you don't pass a conference at all, is either it's really cheap to copy the object, or in new style C++, if you're potentially taking ownership of that object. So for example, if somebody says, I'm totally done with this, I'm not going to use it anymore, I'm handing it off to you, it's now your responsibility. If I'm the function who's taking that thing handed off to me, I'm potentially taking ownership, and that's when I might do this. Okay, the standard library. We're almost to our ugly section. We're getting there. So most languages, I've been picking on Java. Java has a fantastic standard library. It gives you so much functionality. There's sockets, there's everything. In C++, we have almost nothing in the standard library. It is itty bitty. And that's actually kind of C++'s weak point. And it's getting better, but we're still decades behind. So traditionally, the solution to this is we use separate libraries, something else. If we need a socket, we go find a socket library. The standard library is huge, despite me just saying how tiny it is. It's tiny compared to Java, which is astronomical. But despite it being huge, I only want to focus on 3 things for now, because I don't have a ton of time. So I want to talk about string, vector, and smart pointers. The string, you're familiar with that. I would say std for standard string, dog name equals Fido. Vector is just a way to have some contiguous memory, and it's kind of like, I don't want to use the word list, but it's just an array. It's closer to an array, but it can dynamically grow and shrink as needed. So here I have a standard vector of integers, and I just initialize it, 1, 2, 3, 4. And then I could also kind of combine these. I have a standard vector of strings. So now I'm containing the names Amy and Rick. So although I'm only showing you these three things, there's another piece of the standard that is actually not widely used, but we should all be using it a lot more. I think this is because if we took C++ class in college or something, we were all asked, write this function that's going to loop over this stuff and do these operations. And so we got used to writing the thing that's actually already written. For example, there's a standard sort. People don't use it for some reason. I don't know why. Same with standard copy if. So you can pass in a a predicate, and say, if the value passes my predicate, my test, if I want it to be like values less than 10 or something, if it passes the predicate, then copy. Otherwise, don't. So there's a whole bunch of things in the standard algorithms, not just these standard containers, but people don't use them often. So I encourage you, if you want to look like a really smart C++ programmer, start using standard algorithms. People will be impressed. All right, smart pointers. So you've maybe heard about pointer. Oh, question. Yes, there is a website, cppreference.com. It is fantastic. It goes over everything, including like this function was added in C++11, but before it, you had this other function instead. So that website contains everything about the language, the standard, and it's broken down into chunks where you can sort of navigate to where you want. Great question. Okay, show of hands, who here has heard of pointers in C++ and heard like horror stories or like battle scars or something? Everybody. Okay, I wasn't expecting it to be that much. Okay, so you get the idea. They're terrifying. So smart pointers aren't those. Those are raw pointers, and we'll get that section later. Smart pointers are sort of like, let's stop terrifying each other. So in a garbage collected language, you're familiar with, if I have a reference, the thing stays alive, and I can have multiple references, and it's still going to be alive until the very last reference goes away. Then the garbage collector has a chance to come and clean that up. In C++, that would be a standard shared pointer. And you get that from include memory. So this represents like if the object lifetime should actually be managed by multiple things. This is where I need to sort of tell you to be different from what you're used to. If you're used to a garbage collected language, you don't worry about who owns the lifetime. It's just whoever has a reference. But in C++, you really want it to be like this object should only live between here and there, and then it should have that deterministic destruction. And so a shared pointer, a shared lifetime, is actually a really uncommon situation. Even though that's the default in garbage collected languages, that's weird. Typically, like, my car has wheels. It's not like, well, if my car goes away, I still have wheels. That doesn't make sense. So we have this, but we don't really use it that often. You try to avoid it if you can. In fact, if you have to use it, you start questioning, like, did I do something wrong? And although I'm showing you standard shared pointer, we actually don't use that in Chrome. We use base shared ref. It's basically the same thing, though. Okay, yeah, and I told you that most of the time we don't actually want to use a standard shared pointer. So the alternative to shared pointer is unique pointer. Makes sense. There's only one owner. It is unique. And you can't make copies of a unique pointer, obviously, because then you would have multiples and duplicates and shared ownership. So what you can do is move it. And remember earlier when I said, if I'm taking ownership of something, somebody could call my function and pass me ownership of this pointer, and that would still be unique if they no longer have this ownership. So it's all sort of tying together. And then, yeah, when the only reference is destroyed, the actual object is destroyed. So it's kind of like a garbage collected language where you can only have one reference at a time. That's kind of how it would work. Okay, and I mentioned, you can't actually make a copy, but you can pass ownership. The way you pass ownership is with standard move, std move up there. That is a way to say, I'm completely done with this. I'm going to pass it off to somebody else. And if you want to learn more about this standard move and the whole like passing ownership, Here at Google, we have a class for C++ 11 where we cover this. Or later today, I'll be giving a talk called C++ Memory. But if you look at your badges, I changed the title late, and on your badge, it'll actually say C++ 201 Move Semantics. So you can learn more about it then.